I want to optimize some function, let's say of some vector, and let's say that, well, these are some function. We will call this thing that we want to optimize our objective function, and it'll be subject to some constraint, just like the very last problem that we did in the very last section. And so subject to some constraint, let's say g of x equaling 0. We will call this the constraint equation. So let G be a continuously differentiable mapping from an open subset of U of a n plus m dimensional vector space X to a vector space Y, such that the differential of G at A is surjective for every A in the kernel S of G. Maybe I'll say kernel. The zero set S of G. Then S is an n-dimensional submanifold of X. Suppose that F has extreme value on S, point B. Then there is a L, which is a linear transformation from a linear functional, actually, from Y to R, such that B is an extreme point of the new function, F plus G composed with plus L composed with G. Again, remember then as a linear mapping, this will become a multiplication. And so if I look at the matrix representation, this will actually be some F plus L times G. If I call those their matrix representations. So let me restate this in a slightly less general case. So suppose I want to optimize f of x subject to g of x equaling k. Then the gradient of f is parallel to the gradient of g. So that's just a restatement of what this says. So let me again say it a little bit more in a particular case. To find the maximum and minimum values of f of x, y, z, so this is a function just of 3 variables, subject to the constraint g of x, y, z equaling k, assuming that these extreme values exist, and the gradient of g is not 0. On the surface, g of x, y, z equaling k, a. Find all values of x, y, z, and lambda such that del f x, y, z is equal to lambda del g x, y, z, where g of x, y, z is equal to k. And, I should say and, g of x, y, z is equal to k. Evaluate f at all points, x, y, z, that result from step A, finding the critical values of the Lagrange function. The largest of these values is the maximum value of f. The smallest is the minimum of f. Another way of stating this To optimize f at x, y, z, subject to g of x, y, z equaling k, you will optimize a new function, the Lagrange function. F at lambda x, y, z is defined as our original objective function, f x, y, z plus lambda, this Lagrange multiplier, times the quantity g x, y, z minus k. So this is on this level set of g. Or this will be the kernel of this new function if I put the minus k on the other side. So let's look at more than one constraint. So to optimize f at x, y, z, f of x, y, z, subject to the constraint g of x, y, z equaling 0, and h of x, y, z equaling 0. Oh, I just let these. So now these will be, the kernel would be where it happens at the 0 set. Optimize a new function, this Lagrange function, f lambda mu x, y, z equaling the objective function, f at x, y, z plus, oh, I'm doing it as a plus. Okay, that's fine. Plus lambda g x, y, z plus mu h x, y, z. So this changes this constrained optimization to the case that we've seen before in the previous section. So let's discuss the second derivative test. So the second derivative test with m constraints. So we're going to try to perform a second derivative test where we're trying to optimize some objective function on m constraints. So we will form, what we'll call a bordered Hessian matrix, where basically we have formed this Lagrange function, the Hessian for this, and written in this order, the Hessian for this new function is called a bordered Hessian. And the matrix for it is the bordered Hessian matrix. We will disregard the first 2m principal minors. We will then look at the other principal minors after I've disregarded the first 2m of them. So if the principal minors alternate in sign, starting with -1 to the m plus 1, we're at a local maximum. If all the signs are -1 to the m, then we're at a local minimum. Okay. So let's again try to look at this in this case I put a minus. Usually I put a minus, so that's good. So let me look at a more specific case. Suppose I want to optimize f of x subject to, I'll say k constraints. G of L at x is equal to C sub L for L equaling 1 through k. I will form the Lagrangian function L of lambda comma x, where lambda is lambda 1 through lambda k, and x is x1 through xn. And L of lambda x is equal to f of x, our objective function, minus the sum L equaling 1 to k of lambda sub L times the quantity G sub L at x minus CL. So this just gives you what we said above, but now in slightly better notation, where G, of course, is, actually, I didn't use that yet, is G1 through GK, and C is C1 through CK. Assume, I'm going to use it here, assume that F, G, L go from Rn to R, and that these are C2. It's the second derivatives, all the second partials are continuous. Assume that X, and let's put a little star in Rn, and lambda star meet these first order conditions, C, that is, that the differential of L is 0. Once, could you turn off your mic? Let DG denote the matrix representation of DG at this X where the derivative of L is 0, so where it satisfies these first order conditions, and D squared
barked like yesterday as well.
L denotes the matrix representation of what's the Hessian of D squared L. The Hessian matrix L is the bordered Hessian matrix, and we'll denote this. So H is equal to the matrix where this is 0, meaning the 0 matrix, the size so that it makes this an actual matrix, so it fills it in. And it'll actually be how many constraints? K. It'll be a K by K matrix. Minus DG minus DG transpose, and then this D squared L. Then, if F has a local maximum on this surface, this submanifold, basically the kernel of G at X star, then V transpose D squared of L, V being less than or equal to 0 for all V in the null space of DG. If F has a local minimum on G inverse of C at X star, then V transpose D squared L, V is greater than or equal to 0 for all V in the null space of D sub G. We'll get some better conditions on the next step. Once we restate this, these are just statements about the about some quadratic forms. If V transpose D squared L is less than 0 for all V in the null space of DG without the 0 vector, then X star is a local maximum of F on G inverse C. So that gives us a nice little condition here. That's the second derivative test. If V transpose D squared L, V is greater than 0 for all V in the null space of dg without the 0 vector, then x star is a local minimum of f on G inverse C. So that gives yet another case for the second derivative test. And there, lastly, saddle point sort of idea. If V transpose D squared L V is greater than 0 for some V in the null space of DG, and V transpose D squared L V is less than 0 for another V in the null space of G, then X star is neither a local maximum of F on G inverse C, nor a local maximum of F on G inverse C. So it'll be some sort of saddle point possible. Okay, so using knowledge of quadratic forms, we get, so this will be a little, assume that F, GL go from Rn to R, RC for L equaling 1 to K, and that X star, okay, I'm completely black, X star is an Rn, and lambda star is in, I think, RK, right? Yeah, is an RK. Satisfy the first order conditions on G inverse C such that dl, the differential of L, is 0 there. Assume that the K by K submatrix of DG formed by the first K columns has non-zero determinant. And so this assume that this determinant where the determinant of the matrix whose ith jth entry is the partial G sub I with respect to X sub J evaluated at this X star. That's a critical number for the Lagrange function, is not 0 for I between 1 and K, J between 1 and K. Let H sub J be the upper left J by J submatrix of H sub L evaluated at this critical number. If minus 1 to the K determinant H sub J is greater than 0 for J going between 2K plus 1 and N plus K, then the function F has a local minimum at X star on the level set G inverse C. So notice that the sign given by minus 1 to the K depends on just the rank K, the number of constraints, and it does not depend on J. Next. If minus 1 to the power J minus K times the determinant of H sub J is greater than 0 for all J from 2K plus 1 to N plus K, then the function F has a local maximum at X star on the level set at G inverse C. Notice that the sign is given by negative 1 to the J minus K, that this alternates in sign. So we can express this condition as minus 1 to the K times determinant of H sub 2K plus 0, and the rest of the sequence, negative 1 to K determinant H sub J, alternates in sign with J, that this then implies that we have a local maximum for F. Next. If minus 1 to the k determinant h sub j is not 0 for j between 2k plus 1 and n plus k, they have a different pattern of signs than these above two cases, then the critical point is some type of saddle. So where it's type of saddle. Okay, let's look at a few very specific cases. So this will be sort of a cookbook for these last 2 or 3 cases I'm spelling out. So Lagrange multipliers, optimizing a function of 2 variables with 1 constraint. So if you have this specific case of optimize f xy subject to g xy equaling c, let L of lambda xy. Please notice, put the lambdas first. So just remember, write these lambdas first, equaling f of xy minus lambda g of xy minus c. Please notice that well, I'm doing this sign here is sort of arbitrary. It could have a plus or minus, but once you set it, then you can say specifically if you write it this way, then everything has these specific signs, and I can tell you when it's a maximum or minimum when these signs occur. So let's get into the habit, even though I keep alternating myself. Let's get into the habit of putting a minus sign here and having the function. Well, again, it doesn't matter. Having the constant pulled over to the other side. Okay, and so g of xy minus c. Then the Hessian evaluated at the extreme value will have the following form. Well, the Hessian will have the following form, but we'll assume that it's at the critical value. And so it will look like 0 minus a partial of g with respect to x minus a partial of g with respect to y, and it's symmetric. So this side here looks the same as that. And then in here, so remember this was the form 0, and then they had dg, and then it was the dg, the minus dg and the minus dg transpose, and then there was this d squared of L, and so that's going to be this guy here. And so this will be the second partial of L with respect to x, which will include both of these. The mixed partials, and again, I'm going to assume that these are, well, this is the other mixed partial, and then the second partial of L with respect to y. So where this, I just saw something. Where's the C? Okay, the C. Yes, it is. The C is this. So let's see. The last problem, I think it was something like 2xy plus 2xz plus 2yz equaling 64. 64 was that C. It's part of the constraint equation. Okay? It'll give you the level surface. Okay. So where L is evaluated at the critical point, where the critical point is such that the first differential is 0. There it is. X star, comma, Y star, lambda star, with F and G being real valued C2 functions on R2. Let X star, Y star, lambda star satisfy the gradient of F equals lambda gradient of G. Why I didn't put it on the other side, I don't know. Minus lambda is 0. And because it's a critical value. So where this is 0 and G, and maybe I'll even write it this way. G is equal to C, where G minus C is 0. Found, because now I can show you that. Well, let's see. If you take the partial of L with respect to lambda, then you just get, well, this is 0, and this just becomes, this guy is 0. So that's how you get this equation. If you take the gradient of L with respect to X and Y, then you get the gradient of F. This is constant, minus lambda times the gradient of this. Well, this is a constant, so that's 0, so it's just a gradient of G. So that's how you get this term. Then X star, comma, Y star is a local minimum for F on G equaling C if minus the determinant of HL is greater than 0. That corresponds to what I wrote above. So that's why it has that weird sort of minus in front. And this is the HL right here, this bordered Hessian matrix. B, X star, Y star is a local maximum for F on the level set G equaling if minus the determinant of HL is less than 0. Okay. So, and you can think of this, and this also gives you the way we usually state the second derivative test in a one-dimensional sort of case, that if it's greater than 0, it's going up, so it's a minimum, and if it's less than 0, if the second derivative is less than 0, it's a maximum. Let's do the same thing, but just a slightly different case. Lagrange multipliers optimize a function of 3 variables with 1 constraint. So suppose I want to optimize f of x, y, z subject to g of x, y, z equaling c. Again, you form this Lagrange function, L lambda x, y, z. So again, remember, you put the lambda first. If you remember that, then everything else just comes out the same as what you did yesterday and last day before. Equals f x, y, z minus lambda times the quantity g of x, y, z minus c. So let's define the following, again, which are evaluated at lambda star, x star, y star, z star. So I guess I'll call this h sub 4, because it's 4 by 4 matrix, and h sub 3, because it's a 3 by 3 matrix. So again, notice 0, then minus gx minus gy minus gz, and then the same thing on this side. L, so again, just like before, you do xx, xy, xz, and then yx, yy, yz, and then zx, zy, zz. Let's call 8 sub 3. So I'll have to look at the two cases. So first, sort of get rid of, let's see, so z. So you're going to get rid of, so if the partial of g with respect to x is not 0, the partial g, get rid of the z. So get rid of the z here. So if you get rid of z, that gives you this submatrix here. So I call this submatrix 8 sub 3. If x is 0, g of x is 0, and g of y is 0, then let's get rid of the x. So let's get rid of this guy here. Okay. Of course, there'll be some things that are zero in this, but if, yeah, because that's the other case. Let f and g be real valued C2 functions on R3. Let x star, z star, x star, y star, z star, lambda star satisfy I like to write it the other way, so let's write it this way. Satisfy that the gradient of L with respect to x, y, z is 0, and the partial of L with respect to lambda is 0. With the gradient not being 0. Otherwise, this function, everything's going to be 0. It's a constant function. So then, hopefully, if I didn't state that, I hope I did state that above, that we're assuming that we're not at a place where everything's going to be constant, because then it's trivial. X star, Y star, Z star is a local minimum for F on G equaling C if, so in this case, I have to have two conditions. Minus the determinant of H3 is greater than 0 and minus the determinant of H4 is greater than 0. X star, Y star, lambda star is a local maximum for F on G equaling C if minus H3 is less than 0, and now I have to alternate, and minus determinant H sub 4 is greater than 0. And well, X star, Y star, Z star is neither a local maximum nor a local minimum for F on G equaling C if is a type of saddle if minus determinant of H sub 4 is less than 0. Let's look at, so this is another case where I'm just going to do a sort of a cookbook. Lagrange multipliers optimizing a function of 3 variables with 2 constraints. I want to optimize f x, y, z subject to g x, y, z equaling c1, h x, y, z equaling c2. Let lambda, again, notice the order, let L be a function of lambda mu x, y, z. So again, remember to put these first. If you remember to put those first, everything else should work out the way you think it should work out. So let this L equal f x, y, z minus lambda of the quantity g of x, y, z minus c1 minus mu times the quantity g of x, y, z minus c2. And let us define the following, which is evaluated at lambda star mu x star y star z star. So h sub 5 is equal to, well, you'll have a 2 by 2. You have two constraints. So this is this 2 by 2 zero matrix. And then you have this gradient of G, this gradient of H, and then again, minus the gradient of G, minus the gradient of H here. And then you have this Hessian of L respect to X, Y's, and Z's. Let F, G, H be C2 real valued functions on R3. Let X star, Y star, Z star, lambda star, mu star satisfy. I'll just let it equal that. Gradient of F equals mu gradient G plus lambda gradient H. G equaling C1, H equaling C2. Then X, Y, Z star is a local minimum for F on G equaling C1. H equaling C2. If minus 1 squared determinant H sub 5 is greater than 0, and B. One second, let me clean up before I say what is a true statement. Obviously, this was a typo. So X star, Y star, Z star is a local maximum for F on G equaling C1, H equaling C2, if minus 1 squared determinant of H sub 5 is less than 0. Notice in this case, you only needed, I should say that why, because you have 3, actually, let me do this. Even though I said it, it may not have resonated in the general case. So notice I have 3 variables, 1 constraint. So that means I'm going to have to look at 2 conditions. So if you look here, I have 3 and 4. So I have these 2 sort of conditions I have to look at. Whereas here, I have 3 variables, 2 constraints. 3 minus 2 is 1. So I only had 1 condition to look at. So I just had this 1 condition. Okay? So even though I said it in the previous cases, it probably didn't sink in until you show it in explicitly. Okay, so calculus of variations. Suppose I want to optimize J, and it's a function of Y. Well, Y is actually a function. So it's a function of a function. And suppose that I define this as being the integral from x1 to x2 of f of x comma y of x comma y prime of x dx. And suppose I have some conditions. Say eta of x1 equals eta of x2 is equal to 0. Then the differential that we defined a few sections ago, dj, is just equal to the integral from x1 to x2 of the partial of f respect to y, h plus the integral from x1 to x2, the partial of f respect to y prime, setting the differential. And so integrating by parts, I get the differential, and using the fact that these are 0 on the boundary, it'll make integration by parts easy because the first term is just going to be 0. Then the differential of j is just the integral from x1 to x2 of the partial of f respect to y, the derivative with respect to x of the partial of x of f respect to y prime, that third variable, at h times h. So if this is 0 for all h, then that just says that this must be 0. And we'll call those the Euler-Lagrange equations. Let's do some examples. Some of the algebra is going to be a little sticky. Oh, did I? Oh, I wonder if I didn't erase those. Okay, I wonder if I should just do that. So, page 1017, problems 3 through 14. Each of these extreme value problems has a solution with both a maximum value and a minimum value. You use Lagrange multiplier to find the extreme values of the function subject to the given constraint. Okay, so there's C2. Maybe I will just get rid of this. Okay. F of xy is equal to x e to the y and is subject to the following constraint: x squared plus y squared is equal to 2. So I want to form a Lagrangian. L of lambda xy. And so I'll call this f of xy minus lambda g of xy minus c. Okay, so L of lambda xy is equal to, in this case, x e to the y minus lambda g, which is x squared plus y squared minus 2. Basically, you're finding the 0 set of this constraint equation, of this constraint function. Okay, so now let's determine the critical values. So determine critical numbers. for the Lagrange function. So what we have done is we have changed, well, let me recall in the very last section, we did a problem where we're trying to optimize some function. I think it was, we had a sphere and we had a rectangular parallelepiped that was, so we had some optimization function, I think X, Y, Z or something, and it was subject to some constraint equation. Something like that. So somehow we were trying to optimize this function subject to these constraints, and what solved for one of the variables and eliminated it, and somehow made it another function of G, of X and Y. Okay, and then we did it. So this is an alternative to doing that. It will now say, well, instead, let's create this new function and just optimize that new function. Okay, so let's do this. So let's determine the critical numbers. So meaning I want to look when the Lagrangian is 0, or when the gradient of Lagrangian does not exist. Okay, so let's take the partial of L with respect to lambda. That's 0. This will be a minus x squared plus y squared minus 2. The partial with respect to x. Let's just get rid of the stuff. Okay. Partial with respect to x. Partial with respect to y. X e to the y minus 2y lambda. Partial with respect to, that's it. Okay. So first, let's check when the gradient is 0. So let's set each of these equal to 0. I'll just change the sign here. So this just says that x squared plus y squared equals 2. That's the first condition. The next I have here that, let's look at the last one. So last one says x e to the y lambda y 2 y lambda is 0. And I'm going to want to make that. So let's multiply this by x. Okay. And I have e to the y minus 2x lambda is 0. Let's multiply this by minus y. And so I get x squared e to the y minus y e to the y. These will cancel, equals 0. And so I have x squared I have, okay, I have a blank screen. I have x squared minus y e to the y equals 0. Okay. Well, e to the y can't be 0. Y is equal to x squared. Okay. Well, okay, so y is equal to x squared. And so let's try to solve that. Oh, let's get rid of that. So if y is x squared, well, I also had this condition here. X squared plus y squared is 2. So this says x squared plus x to the 4th is 2. And so I have x to the 4th plus x squared minus 2 is 0. I can factor this. Oh, it would have been easier if I would have replaced, actually it's easier, not that it's easier, but it looks nicer. It looks nicer if I do this. Let's replace x squared up here by y. So it's y plus y squared equals 2. Everything will come out the same, but it just looks a little cleaner. So this is y squared plus y minus 2 equals 0. And so I have y plus 2, y minus 1 is 0. So this says that y equals negative 2, or y is equal to 1. But then this says that x squared is negative 2, and I don't want x squared to equal negative 2. Or that x squared equals 1, and so x is equal to plus or minus 1. Okay, so I have the critical values being, I forgot, 1 at negative 1, 1, and at positive 1, 1. Now let's look when the gradient doesn't exist. Well, this is just a polynomial times e to the, so this gradient either involves polynomials or exponentials times polynomials. So this is going to exist everywhere. And so therefore, we don't get anything from having the gradient be not existing. And so that says that my critical numbers, my possible extrema, it's kind of weird to call a point with two variables a number, but that's what they are. Okay, so now let's get rid of that. Let's have some room. Let's actually figure out, actually I don't have the critical numbers yet because I don't have, those are the only x's and y's. Wait 1 second. I don't have what lambda is yet. So let's actually figure out the critical numbers. I haven't done that yet. So now let's figure out what lambda is. Okay, so let's see. So let's determine lambda. At -1. So let's figure out what that lambda is. Okay, so we have here, let's say e to the y minus 2 lambda x is 0. So that's one of the equations that we had. There it is right there. That's the first equation here that you saw going by really fast. So I have this equation here. So let's use that to figure out what lambda is. So this gives me e to the 1 minus 2 lambda -1 is 0. So lambda equals 1/2 e. Yeah, good enough. So minus 1/2 e. Okay, let's see what happens at 1. Determine lambda at 1, 1. Okay, so we have, again, e to the y minus 2 lambda x equaling 0. I have that one equation. So plugging in 1, 1, I have e minus 2 lambda equals 0. So lambda is just positive 1/2. Okay, so I have the critical numbers. Are, what are the critical numbers are? -1, 1, -1/2 lambda, -1/2 e, and 1, 1, 1/2 e. So these are my two critical numbers. Okay. So now, since the derivative, and I wrote it the wrong way, didn't I? Here, wait. I wrote this the wrong way. It's minus 1/2 e minus 1, 1 and 1/2 e 1, 1. So those are the critical numbers. I wrote the lambda in the incorrect location. So those are the critical numbers for L. So now, since the critical numbers were such that the first derivative was 0, the gradient was 0, then I can use the second derivative test. I could use the first derivative test. I didn't explicitly write out the first derivative test. It's a little bit more difficult. It's more difficult. But you could do the first derivative test on this, but we're going to just do the second derivative test. I gave you all the second derivative tests, so let's use the second derivative test. So use second derivative test. So this will involve the bordered Hessian. Okay. So let's look. Stop. Just for 1 second, let's copy these. So I can cheat for a second and see what these are. Remembering all the signs is going to be difficult, so stop. Okay, stop. Stop. Let's go back. Oh, that's going to be a delete. Okay, so let's put those there. So let's find L lambda lambda. Well, obviously this is not a function of lambda, so it's 0. Let's do L of x lambda. And so that's a minus 2x. L y lambda. That's a minus 2y. L lambda x. It's a minus 2x. L xx. And so that's minus 2 lambda. L x. I'm doing x now. Okay. So y is just e to the y. Lambda. So these are L lambda. This is y. So lambda xy. Okay, so this is equal to y minus 2y. L. This is the x, y. So y do x, that's just e to the y. L, this is going to be a yy, is, oh, x e to the x, x e to the y, minus 2 lambda. Let me move this a little. Minus 2 lambda. Okay, good. Okay, so I have 2 variables, 1 constraint, so I only need 1 Hessian. So I just need the full Hessian. So all I have to do is look at this Hessian. Actually, let's move it down 1. I'll write 8 sub 3 is actually the determinant of this Hessian matrix, which again is called the Hessian. And so this is going to be a bordered Hessian. And so in this case, it's 0,